हेलो। ठीक ठीक है सर। अभी चालू हो गया। 10 मिनट हो गए।
चैट बॉक्स होगा।
मीटिंग है, ओपन करो पूरा। ये है चैट बॉक्स। ठीक है, इसमें सब आएगा। इसमें सब अपना पूछेंगे क्वेश्चंस। इफ़ यू आस्क देम एनी डाउट
तो वैसे ही पूछ सकते हैं, वीडियो पूछ सकते हो, सीधा ऐसे पूछ सकते हो।
बट वो अनम्यूट करेंगे बहुत सारा हो जाएगा।
ठीक है।
वैसे चैट इसीलिए ऑप्शन
तो चैट में कैसे देखेंगे? मैं क्लास ले रहा हूँ ना, उसके बीच में चैट बॉक्स कैसे देखूँगा मैं?
हाँ
कैसे देखूँगा मैं?
वेट, ये पूरा कहाँ नहीं आ रहा है? स्लाइड, अपना स्लाइड खोलो।
हाँ
शो योर स्लाइड्स।
हाँ
खोलो। दिस इज हाउ वी आर सीइंग।
हाँ यार, आई नो दैट।
Before you start, unmute this. Okay.
ओके
And you will see whatever the questions or whatever the answers they are giving here.
ठीक है, लेकिन ये तो थोड़ा बंद हो जाएगा ना अभी। मैं ये बंद करके लगा सकते हैं ना? क्या F2 इसका नाम F4 है क्या?
इसकी लिंक सही है क्या? क्लास की लिंक
इस पे करो क्लिक।
इसमें ऐसे से उसका
हाँ ट्राई करो। अभी इसका वो देखो, ठीक है ना?
तो इस साइड में ही हो जाएगा। बीच बीच में मैं ऐसे देखूंगा
ठीक है,
चैट
हाँ
बॉक्स। ठीक है,
बीच में खोल देना।
ओके।
अभी एग्जिट करना।
किस क्लास के लिए चाहिए क्या?
जो पहले, हाँ
उनके पास
सेम है।
ओके
5 minutes। Show me the link.
लिंक कहाँ पर, लिंक कहाँ पर है?
नहीं, लिंक
इसमें है लिंक, इसमें हाँ
सेटिंग में भी
यही सेटिंग्स। कीपर जॉइनिंग
हम लोगों ने बैठ में कर सकते हैं।
यू हैव जॉइन
हाँ 2 features
इसमें ऑप्शन इसमें दो
है 2 बजे।
स्टार्ट करें।
आपने आप स्टार्ट कर सकते हैं, वो ज्वाइन कर लिया लोगों ने।
तुम लोगों ने ज्वाइन नहीं किया ना?
हाँ,
क्या उसमें नहीं हो रहा है क्या?
वो शो ही नहीं कर रहा है, ये बता मीटिंग को फोन।
स्टार्ट करो। So someone please comment in the chat box whether I'm audible, please.
You are audible? Yes, we can hear you.
Yeah, okay, fine, thank you. So I'm going to start the class. Can I start the class? I hope people have arrived. So welcome to this week's practical. This week's practical is serum protein electrophoresis. So I'm Dr. Nikhil Chandran K. So I'll be talking about the practical. So objectives for this week's practical, we have 4 objectives. First one is the definition and principle of electrophoresis. So we'll be talking about the principle of electrophoresis and how do you define the electrophoresis. And the second part, sorry? Okay.
Sir, about 30 people have not joined till now, so
you can wait for another 3 minutes.
Okay, I'll wait for another 3 minutes. So let me know.
Chat box खोल के रखो।
okay.
एक मिनट, क्या है आईडी? फिर से रिपीट कीजिए। हाँ, रिपीट कीजिए आईडी। 505 315 589 ये आईडी है, ठीक है। पासवर्ड नहीं, वो नहीं चाहिए, जो लिंक होता है, जो बच्चे ज्वाइन करते हैं वो वाला लिंक चाहिए। अच्छा, ये लिंक है तो हम लोग गो टू मीटिंग में जाके ये आईडी डालेंगे तो वो हो जाएगा। अच्छा, तो पासवर्ड क्या है? AIIMS LT कैपिटल में है।
So I think I can start now. So I'll be talking about the objectives now. So first objective is the definition and principle of electrophoresis. Second one is the components of serum L protein electrophoresis test. Third one is what are the indications of serum protein electrophoresis, and the final objective is how to interpret a serum protein electrophoregram. So can someone tell me the name of this? Can you identify this person? So he has got a Nobel Prize in chemistry for his extensive research in serum protein electrophoresis. He has many discoveries concerning the complex nature of the serum protein. So he is RNA Tiselius. One second. So he's RNA Tiselius. He has gotten a Nobel Prize in the year of 1948 for his research in the same topic that we are going to discuss today. So he could separate the proteins also during that time. So he was almost the one who started this electrophoresis. So what is electrophoresis? That's the first thing we have to discuss now. So what is it? So talking about the electrophoresis, it's the migration of the charged particle under the influence of an electric field. So there is one thing, an electric field is there, and under the influence of that electric field, charged particles are migrating. So many biomolecules in the solution are present as electrically charged. So we can use this feature to make these biomolecules migrate, and thus we can either separate them out, or we can visualize the separation. So if there is a crude mixture of many molecules, charged molecules, and if we apply the electric field, they might get separated with the help of this, or we can actually visualize it also. So that is the function of principle behind the electrophoresis. So that is the definition of electrophoresis. So you have to little bit know about the physics behind it also. So when voltage of V is applied between two electrodes which are separated at a distance of d, the potential gradient which is developed is given by the equation V by d. So if you have a molecule which is carrying q coulombs of charge, the net force that would be generated on this molecule, this charged molecule, would be EQ. So EQ would be the driving force, which is because of the electric field in which the molecule is situated. So EQ drives the charged molecule towards an electrode. So at the same time, there is an opposing force, which is the frictional resistance, which is actually retarding the movement of this charged molecule. So due to the electric field, you have a force which is dragging the molecule towards the electric field, but at the same time there is an opposing force of the frictional resistance, which is actually opposing the movement of these molecules. So frictional force, what all factors are contributing to the frictional force? One is the size of the molecule, shape of the molecule, then pore size of the medium in which, and the viscosity of the buffer. So these are the factors which are kind of retarding the movement. So what I mean to what I am trying to convey is that the net force of these two opposing force is the driving force. That is the velocity at which the molecule would be moving. So there is a positive force, electric field, and a negative force which is opposing it, that is the frictional force, and the net force determines the velocity at which these molecules would be moving in the electric field. That is the only thing you have to know. You don't have to know every single concept here. You only have to know that driving force is the net. So even if the molecules have same charge, they can migrate at different velocities, because the frictional force is also mattering there, not only the charge, electric field is mattering there. So I hope you have understood about that. So what is the principle behind the serum protein electrophoresis? So what the main principle is that at pH of 8.6, that's the pH. So at 8.6, all the serum proteins would be negatively charged. So negatively charged means they are anions, and they are moving towards the anode depending on their net charge. So we can make the serum proteins move towards the anode because they are negatively charged at pH 8.6, and thus we can separate them out. So once they are separated, we can stain them with the help of the dyes like Comasi brilliant blue or Amido black. So we can separate them, ultimately we can stain them, we can visualize them with the help of. So that is the principle behind serum protein electrophoresis. So what are the components of serum electrophoretic setup? So one is a power supply, so you have to definitely generate an electric field, so you need a power supply for that, and you should be having cathode and anode for the charge species to move either towards the cathode or anode. So you need a cathode and anode to make the species move towards either of the electrodes depending on the charge that they carry. Then you have to have a buffer. Buffer has got two functions. One function is it will help in maintaining the pH. As I said, at pH of 8.4 the proteins are negatively charged, so you have to maintain the constant pH so that the proteins will be negatively charged and they will move towards the anode. But at the same time, the buffer would also transmit the electricity. So buffer has got actually two functions. I have only mentioned one function here. It has got actually two functions. One is it would transmit the electricity. Second one is it would help in maintaining a constant pH, which is required for to maintain so that these biomolecules would be carrying a particular charge at that pH. There is a support medium also. So the support medium is actually the matrix on top of which the protein separation is actually happening. So it will be a porous material which is used to separate the serum proteins. So it is the matrix on top of which the protein separation is happening. Then we have loading die. So loading die has got actually two functions. One, it contains a dense material. So it contains glycerol. So it would give the it would provide density so that the serum proteins would settle down in the column, in the well, and so they don't float in the buffer. So this material should settle down. So to make the protein settle down, you use the loading die. Plus at the same time, it has got another important function. You can visualize the protein migration. So proteins would be invisible. So you add the loading die, so you can see the migration of the proteins in the electric field setup. So these are the two functions of loading die. Ultimately coming to the stain. So once the electrophoresis has happened, once the proteins have separated into different bands, you can stain it with the help, as I said earlier, marzipan blue or amido black is used for staining. So we can visualize the fraction after electrophoresis. So you have a crude protein in the initially you have a crude protein. Now we have separated it into different bands, and now we can stain it also. So these are the components of electrophoretic setup. I hope you have understood that. So you see, loading die has got two functions. One function is it provides density. So you add the loading die, you have a sample. Suppose I have a crude protein sample which is containing protein A, protein B, protein C. Okay, so I add loading die to it, and then I load the well. I'll give you an idea about how to load. The final video will be having the procedure of how to load the die. I'll talk about that in that video, but definitely now know that you load the die into the well. So if you have loading die, it contains a material called glycerol. So that material would give density so that these proteins would settle down. They shouldn't float on the buffer. Actually the electrophoresis is happening on top of the support media, inside the support media, which is, I'll tell, you can understand after some time. I'll tell when I'm discussing about it. So please kind of wait for it. I'll tell when I'm playing the video so that I can show you the well, plus at the same time I can show you what loading die is going to do. So please wait till that. Right now know that loading die, it's a die, so it can be used for visualizing the protein migration. The dense material thing I'll tell you in the last video. I mean, when I'm discussing about the setup in the video. So next, support media. As I said, support media is providing the matrix in which the protein separation is happening. So what kind of support media? There are many kinds of support media. Basically, we are discussing about the most popular support media that we use. One is agarose. It is a polysaccharide of agarose. So it's cross-linked in nature, and its percentage that we use is 0.5 to 3%. In case of polyacrylamide, it is polymerization of acrylamide and bisacrylamide. So it has got smaller pore size than agarose, and the percentage that we use is 3 to 20%. So this is the things. You just know what is the support media and how is it made. No, you don't have to know the percentage and all. If you want to study, you can study that. So I'll be talking about the common support medias that are used in electrophoresis. First of all, I'll discuss about paper, which is a cheap, fast and simple support media that we can use. It's very cheap, it's simple. Actually, it's a filter paper moist, so you have filter paper dipped in the buffer and it is held between the electrodes. So it's kind of simple thing which is happening, but the disadvantage is evaporation and endosmosis. So right now please hold on, I'll talk about endosmosis in the upcoming slides, so you can know about that in the upcoming slide. Right now consider it as a disadvantage which is attributed to paper electrophoresis. And in case of starch, the starch is not properly cast into a gel, it's actually partially hydrolyzed. So the disadvantage with this, it has got good resolving power, that is one advantage of using starch as the support media, but it has got very disadvantage that you need to be an expert, or you need considerable skill to make a starch gel. So you should be an expert, otherwise it is impossible for you to make a starch gel. So that is one disadvantage of starch electrophoresis. At the same time, it has got good resolving power. Coming to the agarose and polyacrylamide, which are commonly used electrophoresis, coming to agarose, as I said, it is agarose and agarose polymer. So you pour the molten agarose. I'll show you in the last video also how to pour the agarose and into the casting tray. Right now, how will you make the support media? You pour the molten agarose into the casting tray, then you have the agarose gel. So it has got better resolving than starch, and especially it has got endosmosis. So I'll talk about endosmosis in the upcoming slide. So right now, it has got a disadvantage, that is endosmosis, which is happening in the alkaline medium. Lastly, you have polyacrylamide. So as I said, it is a acrylamide cross-linked and polymerized. So it has got very excellent resolution. So you can actually separate the proteins with the help of this, and very negligible endosmosis also. But the issue with polyacrylamide is that the sample requirement is more. You need to have a large sample, and plus the acrylamide is a neurotoxin. So when you are handling it, be careful. Be careful because you are dealing with a neurotoxin. So what are the factors affecting the migration of molecules in an electric field? So one is the charge of the ions. Definitely it's self-explanatory that charge of the ions would definitely, so the molecules are moving in an electric field, so the biomolecule should have a charge. The charge would definitely affect the migration of molecules in the electric field. Next one is the size and shape. As I said, the size and shape of the charged particle will definitely affect the frictional force that they would be experiencing while they are moving in the electric field. And as I said, it is an opposing force, so definitely they contribute to the, they act as a factor in migration of the molecules. Then pH of the medium. As I said, the pH of the medium is very important. You have to keep the medium in a constant pH like 8.4 when you're doing serum protein electrophoresis. pH of the medium is also important because at that pH only all the proteins would be negatively charged. Then strength of the electric field also. So that is the driving force. So strength of the electric field is actually affecting the migration of molecule. So finally, the frictional force, which is actually depending on many factors. One is size and shape, plus size, pore size of the media. Everything is contributing to the friction which is experienced by the molecule while they are moving through the gel. So I hope you have understood that. So coming to electroendosmosis, as I've said, I'll be talking about this. So in a electroendosmosis is also known as electroosmotic flow. So it is due to the presence of charge group on the surface of support media. So the support media which would be containing on the surface some charge group, and these are causing an electroendosmosis. So what is it? What is the principle? What is the theory behind it? I'll talk about it in the upcoming slide. Right now, what are the groups which are causing this electroendosmosis? So that is paper. In case of paper electrophoresis, you have carboxyl groups. In case of agarose, you have sulfate group, and in case of capillary, we have silanol group, SiOH. So I'll be talking about the theory in the upcoming slide. So this is the theory behind it. So you can see the capillary wall here. So I'll be talking on behalf of the capillary electrophoresis, the electroendosmosis. So you can see the capillary, sorry, one second. You can see the capillary wall, and it has got silanol groups attached to it. So they have negatively charged. So they are negatively charged and they are attached to the surface of the capillary wall. So what happens is that the positive, the cations in the solution would come and get attached to this negative charge. So the ionized silanol groups create an electric, so that would create an electrical double layer here. So you have silanol group here and the positive cations are attached to it. So this creates an electrical double layer So at the capillary electrolyte interface, there is an electrical double layer which is happening. Now you apply the voltage to it. Now you are going to apply the voltage to it. So what will happen is that these cations would move towards the negative electrode. If they are moving towards the negative electrode, the solution is actually moving towards the positive electrode, anode, but at the same time this cations are moving towards the negative electrode. So while they are moving, they would be carrying a hydration shell also, so they will cause a retardation, so they will move against the normal flow of the buffer which is happening. So that is what is known as electroendosmosis. So I hope you have understood that. So that is because of the charge group which are present on the surface of the support media. So finally, coming to what will happen if you have done serum protein electrophoresis, you will get 6 groups of proteins. They are classified into albumin, alpha 1 globulin, alpha 2 globulin, beta 1 globulin, beta 2 globulin, and finally gamma globulins. So these are the fractions that you are going to get if you do the electrophoresis at pH of 8.4. You will get these fractions if you are doing serum protein electrophoresis. So I will be discussing about each fraction. So once you have done the serum protein electrophoresis, what you do is that you scan it using a densitometer. So densitometer is actually, once you have separated the fraction, you look at the absorbance of each fraction. So that is what is densitometer is doing. Densitometer actually measures the absorbance of each fraction and give you a graph output, a graphical representation of the absorbance of each fraction. So right now, if you do it, so scanning of the pattern gives the quantitative information. So you can see right now albumin, it has got a high its absorbance is shown like this. Is alpha 1, alpha 2, beta, and gamma. So you will get a quantitative graphical representation of the electrophoresis that you have done with the help of densitometer. So ultimately, the range, you should be knowing the range of these proteins also, but basically you have to know only total protein and albumin. Total protein is 6 to 8 gram per deciliter, albumin is 3.5 to 5 gram per deciliter. Rest of the globulins, you don't have to know its exact value, but just know that from the total protein you subtract the albumin, you get the total globulin fraction. Individual globulin fractions amount you should, there is no need to know, but just have an idea about how much it is. And AG ratio you should know, it's 1.5 to 2.5, it's the normal AG ratio. So you should know the total protein, albumin, AG ratio, and total globulin also, which you can get from subtracting the albumin from the total protein. So what are the serum proteins? So these are the fractions that you would get. So I did not talk about pre-albumin. So pre-albumin is a fraction which is actually anodal to albumin. Albumin is the one which is lying more close to the anode. There will be a fraction which is even more closer than albumin to the anode. So that is pre-albumin. So that contains transthyretin. So I hope you know about transthyretin. Transthyretin is a transporter of thyroid hormone in your body. Thyroid hormone is carried by 3 transporters in your body: transthyretin, then you have thyroid binding globulin, and you have albumin. These 3 are the carriers of so it also carries retinol binding protein. You don't have to know about it, but just know that the pre-albumin fraction, which protein is there, transthyretin is the protein which is present in the pre-albumin fraction. Next you have albumin fraction, then you have alpha 1 globulin. So in alpha 1 globulin you have alpha 1 antitrypsin and thyroid binding globulin. This is the second protein that I was mentioning before, which is carrying the thyroid hormone in your body. Then you have alpha 2 globulins, which is consisting of alpha 2 macroglobulin, you have ceruloplasmin, and you have haptoglobin. So ceruloplasmin is a carrier of copper. Haptoglobin is the one which binds to hemoglobin once intravascular hemolysis has happened. So when inside your vessels, if RBC is ruptured, the hemoglobin gets out, haptoglobin goes and binds to it, and so that they are not secreted to the kidney. So haptoglobin is found in the alpha 2 globulin fraction. Then you have beta 1 globulin, which is consisting of transferrin, which is a transporter molecule of iron. And you have beta 2 globulins, which is the beta 2 microglobulin. And finally you have gamma globulins, which is of immunoglobulins. So you need to know the important proteins which are present in each of the fractions. So why do we do electrophoresis? That's one question you have to address. So it is done as a diagnostic tool to diagnose conditions like multiple myeloma, Waldenstrom's, microglobulinemia. So these are B cell neoplasms. So what happens in this B cell neoplasm, like in the multiple myeloma, it is actually plasma cell neoplasm. So what happens in multiple myeloma is the plasma cell which has undergone neoplastic transformation would secrete a lot of proteins. So normally plasma cell would secrete immunoglobulin, but here the multiple myeloma, your plasma cells would be producing abnormal proteins like immunoglobulin light chains, which are known as Benson's proteins. So you will study about multiple myeloma in the upcoming classes and upcoming semesters, but right now you know that it is a plasma cell neoplasm. And you have other paraproteinemias like Waldenstrom's, macroglobulinemia is also B cell neoplasm. In it, same thing will happen. They will produce abnormal proteins in that. So in order to diagnose this, you just have to do a serum protein electrophoresis. You have globulin fraction is increasing, then you can see that you can diagnose these two diseases. So these serum protein electrophoresis is a great tool in diagnosing these two diseases. Then you have prognosis of multiple myeloma. So what is prognosis? Prognosis, you are giving a expert opinion about how the disease is going to turn. So what is the fate of the disease? You can give an expert opinion based on your medical knowledge. So if you're treating multiple myeloma, whether the treatment is working, you can use serum protein electrophoresis and check whether your treatment is working. Is multiple myeloma getting better or it is getting worse? You can check. So the prognostic, so here you can use it as a prognostic tool. So we can use it as a diagnostic tool and prognostic tool. So next I will be talking about multiple myeloma. So the details you will study in the upcoming classes and the upcoming semesters, but right now you have to have a brief idea about what is multiple myeloma. So as I said, it is a plasma cell malignancy. So usually the B cell is produced inside the bone marrow. Once it gets out of it, it undergoes malignant transformation, maybe because of a DNA damage which is happening. It undergoes malignant transformation. Now right now it is not functioning as a normal plasma cell. Now it is a multiple myeloma plasma cell. So what it secretes abnormal proteins. Plus, so as a result of that, these abnormal proteins are immunoglobulin light chains. So they get secreted, they get deposited in the end organs. Like one of the chief organs where these proteins get deposited are kidneys. So these organs would undergo damage. Other thing which is happening is that these plasma cells would home into the undergoes homing to bone marrow. So once they go there, they cause lytic lesions of the bone. So once you have lytic lesions, bone resorption is happening. So you have fragile bones, you have osteopenia which is happening. So plus your bone marrow is getting destroyed. So you have anemia. So the hemoglobin levels would be less than 10 gram per deciliter. Plus the calcium is going out to the blood. So you have hypercalcemia. So calcium levels would be greater than 11.5 milligram per deciliter. Finally, renal failure. As I said, these proteins are going to get deposited in the kidney. You have renal failure. So how would you know you have renal failure? Your creatinine levels would be higher, 2 milligram per deciliter. Less than 1.5 should be the actually, but you have high creatinine levels here. So just know what are the effects. This is the brief idea you will be studying about in the upcoming classes. So I'll repeat it one more time. You have plasma cell neoplasm which is happening. As a result of that, they are producing abnormal proteins, abnormal immunoglobulin light chains. They are going to deposit in the kidney, causing renal failure. These plasma cells are going to the bone marrow, causing lytic lesions here. So you have osteopenia, plus bone marrow is getting disrupted. So you have anemia. Then the calcium is going out to the blood. You have hypercalcemia. So just know these important features of multiple myeloma. So here is how the densitogram of the multiple myeloma would look like. So you can see here, this is the M spike. So as I said, they are producing paraproteins which are immunoglobulin light chains. So their amount would be very higher in the blood. So they cause an M spike. This is the normal way how a normal serum electrophoregram should look like. But here you have an M spike which is an abnormal electrophoregram. So next I will be discussing about the densitogram of each and every common diseases that we deal with in our medicine. So first of all, acute inflammation. So this is the normal densitogram that I can show you here. So what will happen in the acute inflammation? What is the difference which is happening from the normal state? So as you know, in acute inflammation you have, which is caused due to infection or surgical trauma. So there is an immediate response of your body towards an infection, an acute response towards the inflammation and infection which is caused. So you have albumin there, which is normal or decreased. You have alpha 1 and alpha. So the albumin can be normal because albumin is not getting increased. But why it is lower, sometimes lower, because your vessel walls would be leaky in case of inflammation. So albumin might leak out of the vessel wall, which would cause a decrease in albumin fraction. But definitely the alpha 1 and alpha 2 globulins are higher, because these alpha 1 and alpha 2 globulin, I did not mention it before, they contain acute phase reactants. So acute phase reactants are the proteins which are produced by the liver during the time of an acute inflammation or a chronic inflammation. So these proteins are normally produced by the liver, but during the time of acute inflammation or chronic inflammation, their rate would increase. So that's why they are known as acute phase reactants. So these proteins usually comes in the alpha 1 and alpha 2 globulin fraction. So their levels would go up in case of acute inflammation. So this is how it would look like. So you have higher alpha 1 and alpha 2 globulin fraction. Albumin can be normal or decreased in case of acute inflammation. But definitely when it comes to chronic inflammation, now your body is going to synthesize. Now the system is in a chronic state. So chronic inflammation has been happening for a long time. So in this case, what will happen is that your gamma globulin fraction would also increase. Now the body is synthesizing gamma globulins to fight the infection right now. So the gamma globulin fraction would also increase in case of chronic inflammation. Rest, it would be same picture as like of the acute inflammation. Coming to the third, nephrotic syndrome. So I hope you know about, if you don't know about nephrotic syndrome, it is a disease of your glomerulus. So what happens is that your glomerulus is filtering the blood so that you can make urine, but normally the albumin and all are not getting filtered because the glomerulus, the filtration barrier, contains negatively charged proteins that would repel the albumin back into the blood. But if you lose those negatively charged proteins which are present on the filtration barrier, your albumin would freely go into your blood. So you have loss of albumin, which is happening in nephrotic syndrome. That is the only thing right now you have to know. You will study about nephrotic syndrome in the upcoming classes, but the albumin would leak out into the so you have loss of albumin which is happening here. So what happens is that your albumin fraction would go down, but at the same time, so your liver would synthesize the other proteins, other carrier proteins like alpha 2 macroglobulin and beta globulins. So what happens is that the alpha 2 suppose if I talk about alpha 2 macroglobulin, that is not getting filtered, so the levels of alpha 2 macroglobulin would increase. So alpha 2 globulins are rising in case of nephrotic syndrome. Then gamma globulins would be normal or less. So as I said, albumin would be decrease, there would be a decrease which is observed in albumin fraction, but alpha 2 globulin, which is consisting of alpha 2 macroglobulin, there would be a rise because it is not getting filtered through the kidney, and gamma globulins will be normal or less. Coming to the last one, which is liver cirrhosis. So in this, what happens is that liver is producing all these proteins like alpha 1, 2 and albumin fractions. Albumin fraction and alpha 1 and alpha 2 fractions are produced by the liver, so those fractions would go down. Beta globulins are produced by liver, but at the same time, like C3 complement, you have LDL, etc. in the liver. So these fractions are not produced in the liver. So these fractions would be normal. Coming to the gamma globulin fraction, if the etiology which is causing the cirrhosis is an infective pathology, definitely you have a rise in the gamma globulins. So you have rise in the gamma globulins. Albumin fraction, the proteins which are synthesized by the liver is going down here. So we have albumin which is decreased, alpha 1 and alpha 2 globulins decreased. Beta globulins will be normal because they are synthesized from outside the liver also. Gamma globulins, because if you have an infective pathology which is leading to the cirrhosis, you have gamma globulin rising. So finally, this is the easy way to remember. So you can remember using your fingers. This is the albumin fraction. You have alpha 1, alpha 2, beta and gamma. So with the help of the finger, you can remember the fractions of electrophoresis. So next I'll be showing you the video of how to perform the practical. So I'll show you the video right now. So if you have any doubt, please ask.
Sir, why liver cirrhosis beta globulin level increased?
No, it's not increasing. Beta globulin levels are normal.
So why it remain normal?
Because the alpha 1 and alpha
Why is beta globulin?
see, the alpha 1 and globulin alpha 1 and alpha 2 fractions are produced by the liver, so those levels will go down. But beta globulin contains other proteins also which are not synthesized by the liver, so so their levels might not go down. You understand? Beta globulin is also produced by other sources. Okay, like we have C3 complement in that is not produced by the liver, so those levels won't be affected, those proteins levels won't be affected in cirrhosis. But in case of alpha 1 and alpha 2 globulin and albumin, those levels would be affected. So I hope you've understood that. Yes?
Yes, sir.
Okay. So I'll be show you the video of how to perform the practical. So I'm going to show you how the practical is to be done. So you have you are going to perform serum protein electrophoresis here. So it is done with the help of agarose. So I have measured the quantity of agarose. So we are going to make 1.2% agarose gel. So I have taken barbiton buffer here. Then you have agarose which comes in a bottle as a powder. So what I'm going to do is that for 30 ml of barbiton buffer, I have measured enough quantity of agarose in the filter paper and I'm going to add that to the barbiton buffer which is there. So right now I'm adding the agarose which is and I'm going to mix it. So as you can see, it is not mixing well, so it requires heating. So I'm going to keep it in the microwave for 5 minutes so that it will be properly dissolved. So next I'm going to show you. So here you have the molten agarose that I kept inside the microwave and it is dissolved properly. You can see it has got dissolved properly. So I would be demonstrating the casting tray. So this is the casting tray. It comes in different sizes depending on the number of samples that you are going to process. So this is a small casting tray. It has got wells in it. These wells you can keep it inside so that you can, so it has got comb in it. You can keep it inside the once you have poured the agarose, you keep it inside so that you can create wells in it. So you have to make sure that the chamber is tight, airtight. Now I am going to pour the agarose into it. So here I am slowly pouring the agarose. So you have to make sure that it is not overflowing. So you pour the agarose into it, you keep the comb there and allow the agarose to solidify. So I'm going to keep the comb now. So this is the comb, I'm going to keep it. So once it solidifies, you remove the comb, you get wells. So you have to make sure it is airtight. Now I am going to demonstrate how you prepare the sample for it. So I have taken serum separator vial and I have collected blood in it. After centrifuging it, I transferred the serum into a new tube. This is the loading dye and I'm going to add both of them and mix them in a separate tube. So then only I'll run the gel. So I've transferred the serum into the serum separator vial. So from the serum separator vial into separate MCT. Now I'm from that vial, I'm going to transfer it to a new MCT. So here I'm transferring the 20 microliter of serum into a new MCT, new tube. So I've transferred serum into a new tube. Next I'm going to transfer loading dye. So I'm transferring around 10 microliter of loading dye also. So as I said, loading dye here would help. So I have collected the serum in it. So the loading dye would help in making the sample denser. So I'll show you the loading part of the dye, loading part of the sample, then you can understand why you have added loading dye. So I'll tell there about it. So right now I'm transferring the loading dye into the new MCT in which I have transferred the serum also. So I'm taking 5 microliter of loading dye So I have transferred to the serum containing tube, and I'm going to mix it well. So I've mixed it well. So now the new tube contains both serum and loading dye well mixed. So that's about the sample preparation. So next I'm going to demonstrate the apparatus. So this is the negative electrode, this is the positive electrode. So I'll be doing this electrophoresis at pH of, it contains buffer which would maintain the pH of 8.4, so that the proteins would migrate from the negative electrode to the positive electrode. So this is the entire apparatus. Once you connect it, you can start running the gel. So this is the agarose after solidification. So you can see I have removed the combs from the topmost portion, so you can see the wells which are formed. I've gotten good wells in it. So right now I'm going to transfer it into the apparatus, and I'm going to start running the gel. So I'm going to transfer it to the apparatus containing the buffer solution. So apparatus is not empty, it contains buffer solution. So I've transferred it to the buffer containing apparatus. Now I'm demonstrating how we load it. So this is where what I have been talking about. So you're going to load it into one well of your casting tray. So here I'm loading it. So this is what I'm saying. Now if you're loading it, the sample that you've loaded should not float. That's why the loading dye makes it denser, so that they will go and settle down in the bottom of the wells. See, they are going and settling down in the bottom of the well. So for that, the loading dye helps in that also. Plus it would give. So I'm going to demonstrate. Finally, I'm going to demonstrate the power supply. So it has got the voltage setup. It has got current setup. So you can set up whatever voltage you require, what amount of current you require for that. And finally, you have to press run and close the apparatus and start the run. So once you have done it and you have stained it with the staining dye, okay, once you have stained it with the staining dye, you will get a picture like this. The gel would look like this. Now if you use a gel documentation system, finally we will get gel picture like this, in which you can see this is albumin, this alpha 1, alpha 2, beta and gamma. So that is how you perform this electrophoresis. So if you have any doubt, please ask me.
So what should we put in the other wells? I mean,
yeah, you can
only one well.
you can put it. You can put in all the wells.
Standard.
No, you can put in the other wells also. I have only used one well. You can use the other wells also.
Yes, thank you.
Okay, thank you. Then I hope you have understood the practical. So thanks for joining.
How that form like led to formation of well?
Sorry.
How that form like structure led to formation of well in agarose?
So that comb, before solidification, you have kept the comb, right? So after the solidification, you just remove the comb, you get the wells, because that part would be not solidified. The place where you have kept the combs, that won't be solidified. Okay, so those function as the well. You remove the comb, that part. Yeah. So thank you for joining the class. It's a Barbiton buffer that you're using at 8.4. It is used to maintain the pH of 8.4. Okay, thank you. Then.
Sir, is there another class after this, or is it over?
Sorry?
Is there any other class after this, or is it over? Like we can leave it?
It's 1 second. I'll let me confirm that. It's over, right? It's over. Done?
Thank you.
Okay, yes. I think it's done.
Thank you, sir.
Okay, yes. Okay, thank you.
Somebody asked electron was also.
Oh, I did not see that.
Explain यार. You ended.
I did not see that. I was answering the other question. Done? How was it?
We are going
Too fast. Fast is the.
even I went process. मैं बीच में एक्सप्लेन करने की कोशिश करूँ मैं खुद को एकदम लीड टू लीड बहुत ज़्यादा Did you get any what is electron induction? मुझे पता चला. That's why. Did you understand? He didn't. Explain it.